relationship between system parameters and pole locations. Here, where is the pole? This is the first system. What is the order of the system? 1. Here, this is also order is first order system. Here also the order is first. Here, location of pole equal to -1. Here, location of pole equal to -1/3. Here, location of pole is -1/5. So, all in the left hand side, therefore, all the three systems are stable. Stable systems. All systems are stable. Because here the pole is at -1, -1/3, -1/5. If you see the response, first order response, this is one, this is another one, this is another one. This is G3, this is G1, this is G2, this is G3. G3 takes a long time to settle. G3 takes a long time to settle because the time constant is large. Time constant is large. As time constant increases, it takes long time. Here 3, time constant is 3, therefore it takes little bit lesser time than G3, and G1 takes lesser time than G2 and G3. It quickly settles because the time constant is 1. For this the time constant is 5, for this the time constant is 3, for this the time constant is 1. So the speed of response is faster if the time constant is less. If you talk in terms of poles, all are real poles. All are real poles. Which is closer to j omega axis? -1/5 is closer to j omega axis. If you plot this, all the three poles, if you plot, this is for G3. This is for pole of G3. This is pole of G2. This is pole of G1. This is 1, -1/3, -1, -1/3, -1/5. The poles are very close to j omega axis. System becomes sluggish. System becomes sluggish. If you talk in terms of poles, if you talk in terms of time constant, that is inverse of pole location. That is, this has time constant 1, this has time constant 3, this has time constant 5. So it takes long time to settle. That is the relationship between the parameters and system behavior. This is sluggish system. G3 is slow system. This is slowest. This is slower. This is, while compare these two, this is smart. Smart, slower, slowest. Because of time constant. If you talk in terms of pole location on the real axis, this is slowest as it is very close to j omega axis. If you take a second order system, this is second order system. What are the location of poles? -b plus or minus square root of b square 4 zeta square omega n square minus 4ac omega n square divided by 2. So if you divide by 2, minus zeta omega n plus or minus omega n square root of 1 minus zeta square. Omega n is taken outside. J, you are taking minus sign also. This is location of poles P1 and P2. Location of poles P1 and P2. If you plot this on this S plane, this is P1, this is P2. What is the distance? This is origin. The distance from here is minus zeta omega n. This height that is omega n square root of 1 minus zeta square. This height. What is the distance here? Square root of these two. That is the distance P1 equal to modulus of P1. Modulus of P1. We can say that the distance from origin, that is modulus of P1 equal to minus zeta square omega n square square root plus omega n square minus omega n square zeta square. These two getting cancelled, that is equal to omega n. Therefore, the distance from the origin is omega n. Distance from the origin is omega n. If you draw a circle of radius omega n, this will pass through P2. This will pass through P2. You will get like this. Am I correct or not? So this circle is called constant omega n circle. Constant omega n circle. Or constant time constant circle, because 1 by omega n is time constant. 1 by omega n is time constant. Inverse of time constant. So if you select at any point, the time constant will be constant along this circular path. Or the circle may be called as natural frequency circle, constant natural frequency circle. Any pole on the circle has omega n of same value. Let it be omega 1. Suppose I am having another system, I am slightly modified this system, got another circle. That is omega 2, omega n2. This is omega n1, omega n2. This is also constant omega n, omega n2, constant omega n circle. If you select any poles in this region, if you select any poles in this region whose natural frequency will be between omega n2 and omega n1. Am I correct or not? If you select some poles in this region, its value will be between omega n1 and omega n2. That we can assure. What is the angle? This angle between this line from origin to that pole 1 is theta. What is cos theta? Cos theta equal to what? Cos theta equal to adjacent side by hypotenuse. Zeta omega n upon omega n getting cancelled zeta. Therefore, zeta is damping factor. Therefore, cos theta is damping factor. Cos theta is damping factor. But theta, the angle is between negative real axis and that line. Line joining origin and origin and pole. The angle is between negative real axis and the line joining origin and pole. Cosine of that angle is called zeta. Therefore, cos theta is the zeta. If you select any point, if you select here, if you select this point, what is zeta? Cos theta. Am I correct? Theta is constant. If you select a point here, But omega n2, omega is varied, but theta is constant. Suppose I am having another system, its omega is omega n3. If you extend that line, same theta. Therefore, this line is called constant zeta line. This line is called constant zeta line. Constant zeta line. So in this line, if you select any pole on this line, zeta will be constant. Zeta will be, theta is constant, zeta equal to cos theta, theta is constant, therefore zeta is constant. That's why this line is called constant zeta line. I am taking another line, that is zeta 2. If you select any point between these two zeta lines, suppose zeta 2 is 0.7, zeta 1, this is zeta 1, that is 0.3. So if you select any pole between these two, I can say that its zeta value lies in between 0.3 and 0.7. Can I say like that? Because this is constant zeta line, 0.7. This is 0.7 zeta line. This is 0.3 zeta line. If I select any pole between these two, its zeta value is between 0.3 and 0.7. If this line means what is the angle? 90. Cos 90 equal to 0. Therefore, zeta is 0. Sustained oscillation. That's why if any poles on the j omega axis, it exhibits sustained oscillation. If you select any point here, it exhibits sustained oscillation. Here, what is the angle? If you select zeta here, what is the angle? 0. Cos 0, 1. Zeta equal to 1. No oscillation. Oh, critically damped. Zeta equal to 1 means critically damped. So if you select any point on the real axis, pole is on the real axis, no oscillation. The pole is on the j omega axis, it exhibits sustained oscillation. In between these two, that is zeta varies between 1 and 0, then it exhibits oscillation. So if the zeta line increases, theta increases, it goes very close to j omega axis, that's why oscillation increases. Theta decreases, it comes close to real axis, that's why oscillation reduces. So it is moving like this. The theta is moving like this. If it is here, sustained oscillation. If it moves away, oscillation reduces. If it approaches this real axis, no oscillation. If it approaches real axis, no oscillation. But no oscillation means all poles must be on the negative real axis. All poles must be on the negative real axis. All poles. If one pole is not on the real axis, means there will be oscillation because of that pole. So all poles on the real axis means no oscillation. Some of the poles are complex means oscillation, because if any complex pole means the oscillation, the zeta value is between 0 and 1, that's why there will be oscillation. So if we have a choice to select the pole means, we can select in this we can define the area under which we have to select the pole. That is called designing. Suppose I want to have a system whose zeta value must be between 0.3 and 0.7. Its natural frequency must be between omega 1 and omega 2, means I have to select the poles here. In this region, if I select, then definitely its zeta value is between 0.3 and 0.7. Omega n will be between omega n1 and omega n2. So I can choose the behavior of the system by selecting the poles. That is called design of controller. That we will see. So we can select the location of poles by simply modifying k. That is also possible. In this system, this is open loop system. Here I am connecting an amplifier. in series with that. Now I made this as a closed loop. I made this as a closed loop. Now what is open loop transfer function? Open loop transfer function equal to kg of s. Am I correct? If two are in series, we have to multiply kg of s. The amplifier and the open loop transfer function are multiplied to the kgs. What is closed loop transfer function? Closed loop transfer function T of s equal to unity feedback. Therefore, n of s upon n of s plus d of s, that is equal to k g of s upon k g of s plus d of s. What is the denominator? K g of, suppose g of s is written like this. Before writing this step, let us write one more step. N of s upon d of s. G of s equal to n of s upon d of s. Therefore, if we substitute closed loop transfer function equal to T of s equal to, what is numerator? K n of s. K is there, that is in the numerator. Therefore, we have to substitute K n of s upon K n of s plus d of s. So denominator is d of s, numerator is n of s. So we can find the closed loop transfer function like this. Now, what is the difference between open loop transfer function and closed loop transfer function? Open loop transfer function is n of s multiplied by k upon d of s. Closed loop transfer function is n of k n of s upon k n of s plus d of s. For both open loop system and closed loop system, if you compare, there is no difference between numerator polynomial. There is no difference between numerator polynomial. But the denominator polynomial is modified like this. In the open loop system, denominator polynomial is d of s. In closed loop system, denominator polynomial is k n of s plus d of s. That is modified. That's why open loop poles are different from closed loop poles. Closed loop poles are moved from different location. Open loop poles are different. That's why if you made the system closed loop, we do not know whether the system is stable or not. Suppose open loop system may be stable. Open loop system may be stable. After making closed loop, we do not know whether it is stable or not. That's why we have to check. After making closed loop, we have to check the stability. We have to check the stability. But we can locate the pole by adjusting k. Because if you change the value of k, the location of poles are changing. The location of poles are changing. If you vary k, for each value of k, you will get different poles. If you vary k from 0 to infinity, you will get infinite number of poles. Suppose if it is third order system, for each k, you will get 3 poles. As k varies from 0 to infinity, you will get 3 sets of infinity poles. If you vary k, if you plot the poles, because if you vary k, poles will be varying. If you plot the poles, then it is called root locus. Locus of poles are called root locus. Locus of poles are called locus of poles as k varies from 0 to infinity. Locus of poles as k varies from 0 to infinity. Locus of poles as k varies from 0 to infinity. Locus of poles as k varies from 0 to infinity are called root locus. Root locus. Locus means path. Locus means path. Locus of poles. The path, the poles are traveling in a particular path as k varies from 0 to infinity. That path is called root locus. That path is called root locus. For example, I am having a second order system. 1 upon s square plus 2 zeta omega n s plus omega n square. This is second order system. Its poles are, these are all the poles of open loop system. open loop system, or let us take, this is closed loop, T of S. What is the open loop transfer function of this? So if you are taking a second order system, it is a type 1 system. That's why one pole is here, another pole is here. If you vary K, the amplifier gain from 0 to infinity, the locus are moving each other. At one point they are meeting each other. After that they are breaking away. One goes up, another one goes down. This is the root locus for second order stable system. Second order stable system. What is the root locus for first order system? What is first order transfer function? G of S equal to K upon tau S plus 1. What is closed loop transfer function? T of S equal to K upon tau S plus 1 plus K, or S equal to 1 plus minus of 1 plus K upon tau. If you vary K from 0 to infinity, it varies from minus 1 by tau to the initial pole is minus 1 by tau, because open loop pole is minus 1 by tau, minus 1 by tau. As you increase K, it moves away, it moves away, it moves towards infinity, this way. As K increases, the locus of pole is towards infinity. Therefore, if you see the second order system, it vertically moves upwards, it vertically moves downwards, another path. If it is first order system, it moves towards left, it never crosses j omega axis, never crosses j omega axis. Whatever may be the value of K, the poles will be in the left hand side only. Therefore, for first order system and second order system, you can increase K to any amount. You can increase K up to infinity. But from third order onwards, suppose I am having a third order system. This is the third order system. If you increase K, what will happen? This pole will move towards left this way. This will move this way, and this will move this way. So at a particular value of K, it crosses j omega axis from third order onwards. Third order onwards. This is the root locus for third order. Fourth order, suppose I am having a fourth order system. Two poles are here, another two poles are here. What is locus of poles? For each value of K, I have to calculate the poles I have to plot. Is it possible? No. That's why there is a procedure to draw the rough root locus. Why we need a root locus? We want to know whether it crosses j omega axis or not for a given value of K. Because if it crosses j omega axis, then the system becomes unstable. That's why I have to check whether it crosses j omega axis or not. To find that, I need a root locus. For what value of K it crosses j omega axis. At this point, if you know the pole, at this point you can find the value of K. That value is called K max. After that it becomes unstable. At this point, if you find the K, that is called K max. After that it becomes unstable. So I can find the maximum value of K so that I can keep the gain of the amplifier within that value, so that I can keep the value within that value. That is called, what is P controller? P controller is nothing but amplifier. We have seen. If you put a P controller, the amplifier gain must be restricted to some value. After that it becomes unstable. That's why finding the value of K is called tuning. Tuning for a particular process. For that, this root locus will be useful. So how to draw root locus if it is more than second order? For that, there is one condition called Evans condition. We have to know that condition. If you use that condition, we can draw the root locus. Let us see what is Evans condition.